This video is on the angular momentum of a non-curving object. And this is a little bit of a strange idea on its face, perhaps, because whenever we think of angular momentum, we think of things curving, going in a sort of circular path. But we can consider an object that's moving in a straight line to have angular momentum. According to this equation, there are actually several versions of this equation, but this is the one that I'm going to give you. The angular momentum is equal to the mass times the velocity times the perpendicular lever arm, you might say. We're going to give you an example of this at the bottom. The point here is an object that's moving in a straight line can be considered to have angular momentum about any point that we want. Let's see if we can get our minds around this with this example here. You can see the picture on the right there, and we have several masses. We're on a Cartesian coordinate system. Here's the origin right there, and the direction of the velocities is given by these bold-faced arrows here. The masses of each object are given right there. Their velocities are given there. And what we want to know is, what's the angular momentum of each of these masses about the origin? That's key, because it matters what point we're talking about. What we're going to do is we're going to use the equation that we wrote up there at the top, m times v times r perpendicular, and let's see if we can work that out. The first one has a mass of 2. That's going to be this one right here. Put a big 1 right there. Mass of 2, velocity of 4. And what's r perpendicular? R perpendicular is the perpendicular distance there. In other words, the r that is at right angles to the v, which is 1 meter. And so that's 8. And what's going to be the unit for this? The unit is going to be whatever the unit is that comes out on the right side of this. Mass is in kilograms. Velocity is in meters per second. And r is in meters. Kilogram meters squared per second. And whenever we come up with an answer, we always put units. Sometimes we get a little bit lazy when we're doing the work and we don't write the units, but we check them before we do that to make sure that they're right. But whenever we write an answer, you always put units on those. And angular momentum has a direction. You can see from the picture here that the direction would be in the counterclockwise direction, kind of like that. Even though this mass isn't moving in a circle, its direction of angular momentum is in the counterclockwise sense. The next one is over here. It has a mass of 5 and a velocity of 2. Mass of 5, velocity of 2. And what's the r value for that one? It's the perpendicular distance between that velocity vector and the point that we're interested in, 5. 50 kilogram meters squared per second. And isn't that also going to be counterclockwise? I'm going to scribble this off. I'm going to say counterclockwise. I'm going to say this is counterclockwise. How about the next one? The next one has a mass of 1, a velocity of 6. And where is that one? That one's right here. Look at that one. That velocity vector goes right through our point. So the value of r perpendicular is 0. Nothing there. And then how about the last one? The last one has a mass of 3, a velocity of 3, and what's its r perpendicular? It's this one right here. So r perpendicular, remember, is the perpendicular distance between the velocity vector line, which is going to be 2. So what's that? 18? 18 kilogram meters squared per second. And think about it a bit, about the origin, that's going to be clockwise. If we consider the angular momentum of all of these, if these 4 constitute the system, The angular momentum of the system about the origin is then just the sum of all these. So that's 58 in one direction and 18 in the other direction. So that means 40 in the counterclockwise direction. Counterclockwise wins.